A couple of viewers have asked how you go about setting up this Tektronix 570 curve tracer and how you make the connections, which are done on a panel down below. Now, I've done a number of videos on this, and I don't think that so far I have actually explained in any kind of depth how you set these various operating controls, the plate sweep generator, the operating voltages, and the X and Y grid step and CRT display and so on. So this video is mostly going to be about how you set up, or at least how I set up, a Tektronix 570. And I have to admit that this is mostly a learn by doing. I could not find a setup book for a 570 anywhere. So basically what it amounts to is there is a small description of setup for one tube in the manual that came with the 570. But other than that, you're sort of on your own. So let's take a look at what your options are and how this box works, and see if we can figure out at least a system for making the appropriate connections and setting the appropriate operating controls. For those of you that want to follow along on this, I suggest you look for a Tektronix 570 manual. Now, this is just a Google search, and the particular search I'm going to click on is this TechWiki. And you will see a screen with the 570 on the right. And what I'm going to do is scroll down to this area, and you will see over here that there are various Tektronix 570 manuals that are shown. So you might want to click on any one of these. They comment good quality, mediocre quality, and so on. I found them all to be readable. But this is one source. There are other sources. You can go to the Bama Manual Archive and other places and look for it. But basically, this will give you something in case you would like to follow along in the original Tektronix manuals. So before we actually look at the mechanics of the 570, let's consider the general case of a vacuum tube. Now, we know that in order to make a vacuum tube operate, you need to have some source of electrons, and that requires generally that you heat up a cathode. And so there is usually a heater or a filament that you have to supply voltage to. Then there is a cathode which emits electrons. Then you have a series of one or more grids in most vacuum tubes, although there are some that have no grids called diodes, but we're not going to consider those here because their characteristics are fairly straightforward and don't require a sophisticated instrument like the 570. So most tubes have at least one control grid, and that makes it a triode. Some of them have a screen grid, which allows the causes the tube to be called a tetrode and allows for higher plate resistance and some other good characteristics. And finally, there is usually either a suppressor grid or what are called beam-forming plates that make the tube into either a pentode or a beam power tube, and finally a plate to attract the electrons from the cathode and through the various grids. So this is what we have to work with. Let's now take a look at a particular tube. In this case, it's a 6W6, and it is a beam power tube. Let's zoom in on the basing diagram. You notice that it has essentially three grids and a cathode. the cathode and the third grid are connected together, and that's fairly normal. The heater is between pins 2 and 7. The plate is on pin 3, and the suppressor grid, the screen grid is on pin 4 and the control grid on pin 5. So how do we go about hooking this up? Well, before we get there, why don't we take a quick look at a block diagram of the 570 and see what it makes available. So here is a 570 block diagram. First, I'm going to zoom in on this left-hand portion. It contains a number of circuits that I'm not going to describe that basically produce a step signal at the output of this step amplifier. That step signal is normally applied to the control grid of the tube under test. There usually is also a DC circuit that provides a DC voltage, and in this particular case it's connected to the screen grid. And then there are two circuits that are connected to the plate. One is this plate sweep generator, and the other is this horizontal amplifier. So, set up as shown in the block diagram, the horizontal display will be displaying the sweep voltage on the plate. The vertical amplifier can select between either showing the plate current, and the reason that it's plate current is the current that is flowing through the plate sweep generator to the plate goes through this resistor. So the voltage across this resistor represents the plate current. It can also display the screen voltage. Notice that here that it's connected to the DC circuit, which is basically connected to the screen grid, or it can display the grid. Now, if it displays the grid, that shows whatever the grid current is. Generally, this is configured with the vertical amplifier connected to the plate connection so that it is displaying in the vertical direction the plate current. Now let's take a look at our hypothetical tube. So here we see that we have connected the filament to a filament transformer inside the 570, and by the way, there's only one of these. So while you can heat the filaments of two tubes at the same time, they have to be at the same voltage. I did a video on how you can use an external transformer to work with two tubes that have different filament voltages. But normally, if you use the internal filament transformer, they have to have the same filament voltage. The cathode is normally connected to ground. The grid is normally connected to the step generator. The screen grid, that's the control grid, is connected to the step generator. The screen grid is normally connected to a positive DC voltage, and the suppressor grid is normally connected to ground. As we saw in the 6W6, this connection from here is also internally connected to the cathode. And then the plate is normally connected to what is in essence a sine wave derived from the AC line that sweeps the plate voltage. So it's only necessary in a given tube for us to identify these various pins by their pin numbers. So, for example, with the 6W6, we use this pinout, which is in the tube manual. That part is generally pretty easy to figure out. The thing that is not quite so easy to figure out is how you set up these various parameters. For example, what voltage do you put on the screen grid? How many steps and how much of a step, how much of a voltage difference per step do you apply here? And finally, how big a plate voltage swing do you provide? In other words, the magnitude of the plate voltage. Now, you can get some idea by looking, for example, at a characteristic curve that's shown in a tube manual. Obviously, this is the plate voltage, this is the plate current, and so you can see that for the 6W6, you want probably about 250 milliamps maximum plate current, and you probably want 350 to 400 volts maximum plate voltage. And then here are the grid steps. You'll notice that these grid steps this is the zero bias line, minus 2.5 volts, minus 5 volts, minus 7.5, minus 10, and so on. So in this particular case, our step is 2.5 volts. And we have, let's see, looks like 1, 2, 3, 4, 5, 6, 7, 8, 9 steps on this particular curve. So we have to set it up somewhat like that. Now let's go and take a look at the 570 and show how we first wire this up and then how we set the various controls. So now we're back on the 570. Displayed across the vertical is the plate voltage. The horizontal is the plate voltage. The vertical is the plate current, and that is currently set, take my word for it, I'll show you these controls in a minute, to 10 milliamps per division. Now what I'm going to do is move the positioning around to put it over the scale, and we'll turn up the scale illumination here so you can see that a little better. And now we can read this if we know what the maximum values are across in the vertical and in the horizontal direction. So how do we determine that? Well, one of the first things we look at is the voltage that we're applying to the plus DC voltage that we're applying to the screen grid. We read that on this meter, and as you can see down here, we are set to the plus DC position. Now, we can also measure a minus DC, or we can measure the heater voltage. Now, in this particular case, of course, we're using a heater voltage of 6.3 volts. You see it on this knob. And you can refer to the manual. It has a picture of the front panel in case you want to look at this. This is where we set the plus DC voltage, and this is where we vary it. So as I pointed out, I've set it to 250 volts on the screen grid. Now, looking beneath the meter, you see this controls the voltmeter, which you see above. So generally you set that, and once you have the proper voltages set, you don't move this very much. But beneath it, you see the grid step generator. And what I'm going to do is, let me back out a little bit so you can see as I vary the steps. This is the steps per second, and I have it set to 240. In other words, it is stepping at 240 steps per second. Now this is the number of steps per family. And we're going to turn it down, lower and lower and lower, and you notice that the number of steps goes down to only 4 there. I have it set normally for something around here, which is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 steps. Well, okay, that's pretty much what the tube manual calls for. Another thing that we can change, let me zoom in just a little bit on that, is the plate sweep generator. This sets the peak voltage, in other words, how much it is at the far right of the screen, and then this adjusts the series load resistor. We have it set to 1K right now. So right now this is set to display 200 volts on the far right. If we went to 300 volts, you see it goes off the screen, and we would have to change the horizontal and vertical position. Right now we are sweeping the plate to 250 volts, which is also the same value we're putting on the screen grid. Then beneath that, I've already talked about the heater voltage and the way you can set the plus DC volts, and then beneath that is the minus DC control. We're not using the minus DC supply right now. So let's now take a look at how we actually have wired up this tube. On this panel, and by the way, you can change out these the sub panels. So this particular one is set up for an octal tube. Across the top you have heater current or heater connections. You then have the ground for, in this case, the cathode, and then grid A, which is of course on a 6W6. That would be the control grid, which is pin 3. Then you have the plate, which is connected to pin looks like 5. I'm sorry, pin 3 is the plate. What am I misreading this? Yeah, I misread this. The plate is pin 3. The control grid is pin 5. And that is this. You may notice down here it says 5. Maybe hard to read inside there. And then the screen grid is connected, that's pin 4, is connected over to the plus DC supply. Let's move this just a little bit so you can see that right here. So to set up the 6W6, we make all of the necessary wiring connections for what we are interested in looking at. In this case, we are displaying what is normally called the average plate characteristics. In other words, we're looking for plate voltage along the horizontal axis and plate current along the vertical axis, and we are stepping the grid from a particular value up. Now, the 570 has a 0 grid switch. It's a push button switch. When you push it, well, let me make sure I'm doing this right. I'm sorry, I pushed the wrong one. The 0 bias switch is there. Now, you see that is zero bias. And that is the characteristics then of the tube. Let me back out just a little bit. Once again, zero bias and the full average plate characteristics for the 6W6. Now, there are other ways you can use the 570. This is the most common way. However, you can use it to display other characteristics, which I'll take a quick look at in the manual, and then we'll close out this video, which I hope has been helpful for those of you that are interested in a 570. But I will encourage you to get if you're interested in the 570, get the manual and read it. It has a much better description than I could give, and it's laid out with diagrams that make it much more understandable. To give you an idea of some of the other ways the 570 can be used, here is a page from one of the 570 manuals. There's an operating manual and a maintenance manual and so on, so it does vary. And at the top, you see the typical curves for a triode and for a this is a 12AU7, I think, in figure 1. And once again, these are the standard plate characteristics. But notice that in this figure, what we're displaying is what is grid voltage versus plate current curve. In other words, with the plate voltage held constant. And you notice that these are used for determining transconductance figures for a tube. Once again, I suggest you read the 570 manual if you're more interested in this. I'm just here trying to show you the flexibility that you have in the 570. Here is a pentode, and what they are displaying is the screen grid current. In a pentode, if you allow the screen grid to be more positive than the plate, say when the plate is in one of its lower voltage states and the screen grid is at a fixed value, the plate voltage can fall below the screen voltage. In that case, substantial screen current can flow. And this is a set of curves that show how much screen current flows under what conditions. And finally, on the right, for those of you that only live in transistor land, this is actually the characteristic of a germanium diode, showing its forward voltage characteristic. Yes, you can actually display diode and even transistor curves on this 570. It's not optimized for it, but it can be done. You need to be careful because there are very substantial voltages available in the 570 that can overload many transistors. Now, here is a particularly interesting curve of screen current versus plate voltage with positive bias. And I am not using positive bias in the demonstration I did earlier. You may have noticed it only goes to zero bias. But some tubes are operated in class A, B, or even class C, where you actually do draw grid current. So, what I've been trying to show is how to use the characteristics of the 570 to learn about particular tubes, Generally, it is used for two functions. One is to get the characteristics of a particular tube under a particular set of operating conditions. And second, it is often used to compare two tubes, and that's the reason why that there is a switch on the front as well as space on the panel for two tubes, so that you can switch back and forth between the tube on the left and the tube on the right. The one we looked at just a little bit earlier, we just used a single tube, but we could have put another tube in the right socket and wired it up, and then compared the two by switching an A-B switch on the front panel. I hope this has been helpful to those who might have wanted to know how you set up a 570. I will confess I have not found a good guide to how to set up a 570. So a lot of what I've shown you is just my own guesses about how I would do that. Obviously, it means getting, in the case of a already known tube, it means using some of the data from the characteristics in the tube manual. If you were working with a new tube, one that you have just made, for example, and by the way, if you want to see some of that, go over to Glass Slinger's YouTube page. He makes tubes, and if you had one of his newly made tubes, you might use something like the 570 to determine what its characteristics are. So, a little bit of a blast from the past, but I'm hoping this answers the viewer's question, as well as any questions that the rest of the viewers may have had about the Tektronix 570 characteristic curve tracer. Thanks for watching. Look forward to some other videos, maybe in a different direction. But in the meantime, in this pandemic, stay safe and have a nice day.